So this is a galaxy image. It's from the Hubble Space Telescope. And I've got a couple of questions for you. If people can just kind of, say out loud what they think. So we've got these questions here on the side. Is this galaxy simply smooth and rounded with no sign of a disk? Or does it have features or a disk? Or do you think it's a star or some kind of weird, image artifact? So does anybody want to venture an opinion? Yeah. You reckon it's got some features? So it's got some kind of structure. Okay. So do you think the galaxy has a mostly clumpy appearance or not really? Not really? Okay. Do you think this could be a disk viewed edge on somehow? Okay, I'm getting lots of no's there. Is there a sign of a bar feature through the center of the galaxy? Okay, that's interesting confirmation for me, actually. I was a bit unsure, but yeah. Yeah, I reckon so too. It's not very strong, but it's just there. And do you think there's any sign of a spiral arm pattern or no spiral? Okay, lots of no's. This is it's actually a fairly complicated one. How prominent is the central bulge compared with the rest of the galaxy? So there's a whole bunch of options there. There's no bulge, just noticeable, obvious, or really dominant. Yeah, okay. Is there anything else that's odd about this? It's kind of hard for you to answer, actually, not having seen a bunch of them. But I'll just tell you, I think the answer is no. It's not particularly unusual. How can you tell? But, yeah. Okay, so a couple of facts. And we go through a similar process again, not necessarily as complicated. Can I get the lights back up again? So I said this was an image from the Hubble Space Telescope. It's actually probably an image that's never been seen before by a human being. So they've collected a lot of data, and they need to process it in some way. And it turns out that for a lot of processing tasks, human beings are still actually better than the best computer algorithms. And so some people at Oxford University in 2007 had the idea of crowdsourcing classification of galaxies. And basically the idea is that you go through a little training process where they kind of test you out, and once you've had a bit of experience, they set you loose then to analyze data. Originally they were doing it from the Sloan Digital Sky Survey, which is a different telescope, and they classified something like 1 million images from the Sloan Digital Sky Survey. Actually, they classified all of the images many times over. They asked people, it's not just one person is shown one galaxy, but I think they ended up actually getting 30 people to classify each galaxy. And they did various things. They would randomly flip the galaxies in case there was some kind of problem in the human visual system in terms of, if there are things like spirals determining whether it's rotating clockwise or counterclockwise. Maybe there's some bias in the human visual system. Actually, they were able, once they backed out the results, to determine that there was a bias in the human visual system. We're slightly more likely to see things going one way or the other. It's kind of an interesting physiological discovery. But the basic point is that the best computer algorithms for doing these kinds of classifications turned out to be not quite as good as careful analysis by professionals. And with the data that they've gathered, they've been able to determine that, in fact, this kind of crowdsourcing, potentially by amateurs, is comparable, once you post-process the results, to careful classification by professionals. In fact, they're using some of the data to train computer algorithms to do a better job than was heretofore the case. So, what we just went through, that process, doesn't necessarily look all that interesting. Why would you go through such a process? So the initial motivation, at least, was a question about whether or not galaxies have a particular preference in terms of handedness. So if you look at spiral galaxies out there in the universe, there's a question, do they tend to look a little bit more, are they pointing in some direction? Is there some slight preference? And there was an astrophysicist in 2006 who had claimed, on the basis of analysis of a small number of galaxies, that in fact there was just a slight preference, but statistically significant, for the spiral galaxy's axes to point in a particular direction in the universe. And if this was true, it was pretty cool. It was not something that was predicted by the standard Big Bang model of cosmology. So it would cause potentially a pretty serious revision to our thinking about how the universe got started. So they started this project, this crowdsourcing project, to try and analyze a very large number of galaxies and see whether or not they could get a more conclusive answer to this question. And it turns out, by the way, that the answer is no. In fact, it was just a statistical artifact. But along the way, they've made many more, much more interesting discoveries, I think, than they originally anticipated. Let me show you just a couple. Oh, I should say, by the way, just want to talk a little bit about the scale. So they started with 1 million galaxies that they were classifying. They've been able to recruit 300,000 people to participate, and so far they've done about 150 million galaxy classifications. Actually, I think they might have gone past 200 million now. So they're doing pretty well. And at peak times, it goes up and down a lot, but at peak times they'll be certainly getting many tens of thousands of classifications per hour, and that adds up. It's certainly better than having some poor grad student sit there doing the classification. There was actually a poor grad student named Kevin Shawinski at Oxford who had sat there for 1 week and did 50,000 classifications, and he went off for a beer with a postdoc at Oxford after that and said there has to be a better way. That's where this project came from. So, some examples of some other things that have been discovered. Here is the Galaxy Zoo forum. We can just get it down. Right. Excuse me. Chace? Right. Okay. It's unfortunately not very easily visible. The contrast isn't quite good enough. It doesn't really matter. There's actually, if you look just here, there's a little green dot in the middle. And so one of the, that's better. One of the Galaxy Zoo forum members, pretty early in the project actually, came onto the forum and said, this is somewhat unusual looking for a galaxy. He wasn't expecting to see a small green a galaxy like this, and asked, what is it? And a few days later, somebody else posted a similar looking galaxy and said, what's this? And then some people were looking at the spectra of the galaxies and noticed that they were pretty unusual in certain ways. In particular, they were able to determine that the galaxies were surrounded by very hot ionized oxygen gas, which is unusual for galaxies. At least nobody had heard of a similar type of galaxy being found. It turned out that they'd actually discovered an entirely new class of galaxy. They're now known as the green pea galaxies. They were actually able to track down. It took, I guess, about 6 or 7 months of pretty hard work. Initially, it was just, oh, this looks cool. Here's another one. Here's another one. Then they started to do some spectral analysis. Then they started to write database queries that would actually pick out from the database possible candidates. And they compiled a list. They looked at them more carefully. They were able to identify about 260 candidate green pea galaxies. Some professional astrophysicists got involved, and ultimately there's actually now a series of papers about this new class of galaxy. So it's pretty cool kind of a thing to have happen, to start with what is this and to end up with that. Here's another example of a similar Discovery. So this is a Dutch school teacher named Henny van Arkel up there on the left. She's one of the Galaxy Zoo participants. And she was looking at galaxies one day, looking at this galaxy, and she noticed, you can just see here, there's a faint glimmer of blue on this image. So she had the presence of mind to post to the forum and say, what is, yeah, that's good. What is this blue gas cloud below? And once again, people kind of batted ideas backwards and forwards, but nobody knew. Professional astrophysicists started to take a look. None of them knew either. And again, we have this interesting situation. Actually, a bunch of papers have been written, some of them with Ms. Van Arkel's name on it. It's okay. So here's one of the first. And they named the object after her, Henny's Voorwerp. She's Dutch. Voorwerp is apparently the Dutch word for object. And at least one of the theories about what it might be is that it might be a quasar light echo. So the idea is that about 100,000 years or so ago, that nearby galaxy contained an incredibly bright quasar, really lighting up the entire region. And in particular, what we now see as the Voorwerp, that blue gas cloud, was actually a nearby dwarf galaxy whose gas was being heated up by the quasar. And what we're seeing is the remnants of that heating. And basically, it's just glowing with the remnants of that energy. And for reasons that nobody really understands very well, the quasar has since turned off. So that's why we don't see it in the galaxy. It's not an entirely satisfactory explanation, I must say. And some people have put forward other explanations. The question is, well, why did it conveniently turn off the quasar nearby? So some people are not convinced by this, and there's a bit of a discussion going on in the astrophysics community. But it's another example where an amateur has kicked off an interesting discovery. Okay, so Galaxy Zoo is just one example of a phenomenon I want to talk about today. It's an example of, I guess, networked science, the use of online tools to do science in new and interesting ways, and in particular to solve problems that just, in some sense, weren't accessible before to scientists. So I'm going to talk about a second example of this. Can I ask a question? Were any of you present at TEDx Waterloo? Okay, good. So you've seen some of what I'll talk about, but not all of it. I just want to get some background. Different people tend to respond in different ways. How many people have a PhD or have published a paper? Okay, all right. It changes slightly, some emphasis later on. How many people have contributed to an open source software project? Okay, and how many people are regularly using open source tools as part of their day-to-day jobs? Okay, not surprising. All right, so my focus is going to be on basic science and talking about the impact of the network on basic science. I'm going to move to a new example. It's a project that was started by a mathematician named Timothy Gowers. So Gowers is a mathematician at Cambridge University. He's one of the world's leading mathematicians. He received the Fields Medal, which is often called the Nobel Prize of Mathematics. And in early 2009, January 27, he put a post up on his blog. Gowers is a blogger, in addition to being a leading mathematician. And the post was entitled, "Is Massively Collaborative Mathematics Possible?" And basically the idea that Gowers was proposing was to take a very difficult mathematical problem, an unsolved mathematical problem, one which he said he would love to solve, and try to attack it completely in the open using his blog as a medium to attack the problem. So the idea was to invite anybody in the world who wanted to contribute to come in and to post their ideas about the problem as comments on his blog. very similar in some sense, obviously similar in spirit to the way in which open source software is developed, although the actual details of the medium are quite different. Ultimately, it would spread out, not just on Gower's blog, but also would spread to a wiki, which I'll show you in a moment. So I want to tell you just very briefly, just to give you the flavor of what the mathematical problem was that Gowers was considering. It doesn't really matter. You don't actually need to know the details, but just to give you the flavor. The flavor is this. He wanted to attack a problem, that the so-called density Hales-Jewett theorem. So what I want you to do is to imagine a noughts and crosses board, just a standard noughts and crosses board, and you're going to fill it up with a certain number of pieces. And you can see that once you fill in enough pieces on the board, in fact, once you fill in 7 pieces on the board, you force a line somewhere, right? There's no way you can fill in 7 pieces without getting a line somewhere. But if you fill in only 6, you can convince yourself, with a little bit of work, that actually it's possible to fill them in such a way that there's no line forced anywhere. So what the density Hales-Jewett theorem does, or it concerns itself with, is considering what happens when you take noughts and crosses board in a very large number of dimensions. So it's no longer 3 dimensions, a very large number of dimensions. And it's not just 3 by 3 by 3 by 3 by 3, but it's actually n by n by n by n by n. And it tells you something kind of incredible. If you go to a very large number of dimensions, the fraction of the board that you need to fill in order to force a line somewhere, so it doesn't matter how carefully you fill it in, there is a line forced somewhere, that actually that fraction gets smaller and smaller and smaller. So you don't actually need to fill in most of the board as you do in 2 dimensions. Instead, in the limit of a large number of dimensions, actually a vanishingly small fraction of the board is all you need to, well, in fact, you're forced to have line even if you fill in a vanishingly small fraction. Right, so this is kind of surprising and shocking, in my opinion. Now, you might say, okay, so what on earth, who cares? It sounds like sort of maybe an entertaining problem, but not necessarily one that's very important. It's difficult to explain why this kind of a result is important. I will say that there were reasons to suspect that it's connected to other results which have been proved over the last 10 years, which concern the distribution of prime numbers. That sounds kind of shocking, right? That there'd be some connection between this geometric problem in high dimensions and the distribution of the prime numbers. But indeed, there was actually kind of an argument to be made, and that's why some leading mathematicians, part of the reason why some of these leading mathematicians are involved. So that's a bit of a digression on what the problem was. Let's get back to the actual kind of the social software or the open source science aspect of it. And you can see, I'll just show you what the discussion looked like. So here's Gowers. He's talking about some of his ideas. He seeded the discussion with a list of 38 ideas about how to attack it. And if you come down here, what you'll see is people, this is actually the start of people's attack on the problem. So the very first person to comment, well, it's actually Gowers himself. He kind of, I guess, for about 7 hours after he posted this initial set, nobody said anything. And then a mathematician named Joseph Solomosi from the University of British Columbia comes in at 9:08 p.m. on February the 1st, 2009, and he writes this comment. And it's an idea. It's a little idea. And then a few minutes after that, Jason Dyer, so this is 15 minutes later, another person, Jason Dyer, comes in. He's got his own little idea. Dyer is, by the way, or was at the time, a high school teacher in Arizona. And then another mathematician comes in, Terence Tao. This is just 3 minutes after that, and he's got his own suggestion. So Terence Tao is actually, he's like Gowers, one of the world's leading mathematicians. He's another field's a medalist. And we're kind of off and running. You can see, actually, if you can't quite see the scroll bar, but we just keep going and going and going, and every few minutes there's another idea comes in. You can see people actually in real time going to bed or waking up or whatnot, because they'll be absent for a few hours from the comment thread. It's kind of fun to go through. Actually, a very interesting thing to do if for people who have some interest in doing research, even if they're not interested in this particular problem, is to read through the comment threads. You're seeing leading mathematicians solve a problem in real time, right? This is not something that we ordinarily get the opportunity to do. It's kind of like, standing over Einstein's shoulder and watching him write in his notebook, or being able to interview him. It's kind of an interesting thing to be able to do, and you start to get a feel for how people think, for how they attack problems. One of the things that is most interesting is to see the extent to which people are willing to just, every idea they chase down. And people make mistakes. They do silly things, they forget things, and so on. This kind of romanticized image that people often have of breakthroughs is not really in evidence. It's very, very hard work on the part of the people involved, and they chase down a lot of either incorrect ideas or ideas which are half-baked and need a lot of modification. You really get to see that in detail. Okay, so this went on through quite a few posts for quite some period of time. There was also, as I mentioned before, a polymath wiki, and this had the function essentially of being a repository. Basically, as people go through these kind of comment threads, they're coming up with ideas and gradually refining the ideas, but it's hard to read through all the comment threads, and a lot of it's fairly half-baked. So what people were using the wiki for was to store kind of useful reference materials and also the progress which had been made, to say, this is what we now know for sure. So after 37 days, Gowers put up a post to say that the problem was probably solved. He ultimately turned out to be correct. They still needed to check over a bunch of things, but indeed at this point they actually had the essential core of the argument. So this was 37 days. During that time they'd had 800 substantive mathematical comments from 27 contributors containing about 170,000 words, which if you've ever tried to read that much mathematics is it's a lot of mathematics. That, by the way, is just on the blogs that were involved. It doesn't include the wiki contributions, which were also very substantial, but which are a little bit harder to count. So, this was really quite remarkably successful, especially for a first shot using off-the-shelf tools. This is a WordPress blog. Really, there are two special things about it. One is that it has a threading plugin, which means that the comments are at least a little bit threaded, and the other is that it has a plugin which allows you to do mathematics on it, so you can get nicely formatted mathematics. And that's basically it. There's actually a funny story about the mathematics plugin, which is it was written by a employee at WordPress, Michael Adams, just kind of for fun, and he has this blog post where he says, I wrote this WordPress plugin that will allow you to do mathematics. I'm sure there's probably only 3 people in the world who care. I don't think he anticipated that this is the kind of thing it would be used to do. So just to give you some idea of where this project has gone, here's the main page of the Polymath wiki, and there have been a bunch more Polymath projects which have gone on, and Polymath-like projects to do all kinds of different things. How many people heard the news? It was pretty widely reported that there was a supposed solution to the P versus NP problem last year. Okay, so most of you. And actually, a very interesting thing happened. Many of the same people who were involved in this first Polymath project got involved in what was essentially a Polymath project to take apart the paper. This, if you look here, where are we? Right. So one of the pages here, the researcher's name was Vinay Dialelaka. So the Polymath wiki was used not actually on Gower's blog, but rather on Richard Lipton's blog they essentially an impromptu polymath project kind of convened there. There were more than 100 mathematicians involved, and they took this 110-page supposed proof and really just absolutely took it apart to find where there were errors, where there were interesting insights, where there were interesting ideas, and people from all over with all kinds of different expertise. There were logicians, computer scientists, there were theoretical physicists involved. There were some people from outside any of those disciplines, and really trying to see what there was in this paper, if anything. And it was much, much faster. After about a week, they concluded that unfortunately the central idea in the paper was probably wrong. I think that's the consensus now. They were able to recover a few small bits and pieces, however, interesting ideas in the paper. Okay. All right, so that's kind of where the Polymath project is at. A couple of notable points. One is that, as I said before, it's very primitive kind of tools, and in some sense that's actually an advantage. It's a little bit like the early days of many open source software projects. Certainly if you look at the early days of Linux, for example, it's people reading mailing lists and then sending diffs via email to Linus Torvalds. This is not a sophisticated kind of an approach, and this has something of the same flavor. It's very much bare bones. The other thing which is, I think, interesting is about the scalability of the approach. 27 mathematicians is a large number for mathematics collaboration, but it's really quite a small number, of course, in the scheme of things, certainly compared with Galaxy Zoo with 300,000 people. And it's an interesting and I think open question to what extent we can scale up. So some of these other projects have involved more people, but we're still not talking about thousands of people. We're talking about maybe on the order of 100 people. So it's an interesting question, how much better we can do than that. All right, so that's a couple of fairly optimistic examples. I want to talk about some reasons for pessimism about doing networked science. So in particular, let me show you an example. So the science journal Nature, probably the world's leading journal, in 2006 conducted a very ambitious experiment. It was what they called their open peer review trial, and they really threw their weight behind it and made a big attempt at this. The concept was that when authors submitted their papers to Nature, they had the option of having a kind of an open peer review process conducted. So the paper would be posted publicly, and then comments would be invited, and there would be an opportunity to rebut, and so on. And what Nature noticed during the period of this trial, it took several months, quite a few people were willing to take them up on it. Authors were willing to take them up on it. There was huge traffic to the site. People were very interested in seeing this, but nobody or very few people were willing to offer comments. Right? And so Nature is a very high visibility example of this, but there are other similar organizations have tried the same kind of thing. So many organizations have tried to build what is essentially kind of an Amazon.com style review system for papers. Similar kind of an idea. You'll have papers in, it's very common in my field of physics, for example. Many people have built sites which take physics papers, often preprints which have just been released by the authors, and give people the opportunity to write comments. And I don't keep track of how many such sites have been started, but at least half a dozen, possibly more. And they all go through the same process. Many people will register for such a site, but nobody, or almost nobody, is willing to actually offer comments. So people want to benefit from the comments of others, but they're not willing to actually offer comments of their own. This is a fairly common problem, unfortunately. Here is another website, the so-called Wiki. It stands for Quantum Wiki. It was started by a grad student at Caltech named John Stockton in 2005, August of 2005. It's a great idea, potentially. He worked in the same field I worked in for many years, quantum information, quantum computation. And his hope was that this would become sort of almost a super textbook for the field. So researchers in the field would come along and they'd put review material, they'd describe the latest open problems, they'd share their ideas about how to solve the problems, and so on and so forth. And he worked very hard with some other people in his lab to seed the Wiki with material, and he did a great job, actually, I have to say. Then he made an announcement at a conference in August of 2005, and I happened to be at that conference. It was at Caltech. And there was quite a lot of enthusiasm, I have to say. Some people were skeptical that this was going to be of any value, but a lot of people were kind of, cool. This would be great. It'd be really good to have sort of a Wikipedia for quantum computing, but at a higher, more technical level. And maybe this could be a locus for collaboration and so on. Well, unfortunately, although lots of people thought it was a good idea in principle, again, nobody really wished to contribute. If you go there today, well, here's the recent changes, and you can see what they are. Life insurance quotes, essay writing tips, so on and so forth, DVD duplication. It's just spammers, right? So there's a lot of good seed material on the Wiki, but unfortunately nobody wished to contribute except, unfortunately, the spammers, which it's been overrun by. So there's a general problem here underlying both these kind of open peer review or open commenting kinds of ideas, the Wiki, as well as many other ideas which have been tried. I'll just mention one other class of ideas. It's the so-called Facebook for Scientists idea. So many, dozens of sites have been started, which essentially the idea is scientists can create profiles for themselves, and hopefully connect with other people with complementary interests in order to share ideas, share data, share code, and so on. And although many such sites have been started, scientists, they're typically ghost towns if you go and take a look at them. So there's a problem here, and the problem is basically if you're a scientist, I'm talking here about basic science, you have to ask the question, why should I be contributing to these sites? It's great, the idea of being able to read the open comment reviews or these open comment sites, but why should you take the time to write a comment on such a site? What's in it for you? So I want you to sort of imagine that you're a young scientist at a university and just think about what the pressures on you are. Typically, for a job at mid-level kind of university to one of the outstanding research universities, we'll have hundreds of applicants. And so it's very competitive. And so people will often spend, as pre-tenure scientists or as before they become assistant professors, they may spend 60, 70, 80 hours a week working on the one thing that they know will lead to a job, and that is building their reputation by getting as many grants and publishing as many papers as they possibly can. And so there's an interesting dilemma here for those people. They may think that a site like the Wiki is a good idea in principle, but that doesn't mean that they're willing to take the time to come in and contribute to the Wiki when they know, I mean, really, the trade-off is this. You can make a long slew of brilliant contributions to the Wiki, or you could write one really crappy scientific paper, and from a career point of view, it is much better to write that one crappy scientific paper, right? And that's a real dilemma. So even if you believe very strongly that it would be great to have a site like the Wiki, for example, function really well, you know that from the point of view of your career, that's just a terrible investment of your time. So it's a very difficult problem to overcome. Now, I talked about these successful examples, the Polymath project and the Galaxy Zoo project, and there are, of course, many other examples. What's going on there? Why were they successful? Doesn't that contradict what I'm saying about the failure of sites like the Wiki? No, it doesn't. The reason it doesn't is because ultimately those other projects are actually quite conservative. Think about a project like the Polymath project. Sure, it's done in a very unconventional way, but the ultimate goal, which was eventually reached, was to write a conventional scientific paper. Right? That's the output from that project. So it's serving the standard career ends. Similarly, with the Galaxy Zoo project, well, if you look at the actual scientists involved, they've written, I think so far they're up to about 30 or so papers using the data generated by the Galaxy Zoo project. So again, you have an unconventional means in service of a conventional end. Okay. But a project like the Wiki or the Open Peer Review project or any of these others that I talked about has the problem that it is not serving conventional ends in any way. And so people are simply not willing to explore these kinds of ideas, or it's very difficult to get them off the ground. So let me tell you about what's probably the most famous example where, in fact, people were able to overcome this conservatism. And that example is actually the case of the Human Genome Project. So there was a pretty big problem in the early 1990s in biology. It was becoming apparent to people that we certainly were going to be able to sequence whole genomes, and optimists at that point were saying we'll be able to sequence the human genome by around 2000, and ultimately they were correct, although there was still some uncertainty. But as a scientist, while it was obvious that that data should be shared as broadly as possible, the data being generated by the Human Genome Project should be shared as broadly as possible, there was a problem, which was, why would you take the data generated in your lab and make it freely available to everybody else? In particular, why would you make it freely available to other people in other labs who are actually your competitors? And so this was a big topic of contention in the early 1990s, and people went round and round and round and round about it, argument after argument. And ultimately there was a meeting convened in Bermuda in 1996, a very important meeting, and many of the world's leading molecular biologists attended the meeting. And basically what everybody said was, look, if we can convince everybody to do it, or compel everybody to do it, to share their data, this would be great. It's obviously the right thing to do, but we have no incentive to do so at the moment. That we have no reason to share our data. We make our bread and butter by publishing papers, not by sharing data in online databases like GenBank. So everybody could see the problem, and they came up with an agreement, now known as the Bermuda Agreement, which stated essentially, first of all, that when data was taken, genetic data was taken in the lab, it should be shared within 24 hours, so uploaded to GenBank or a similar database within 24 hours. And in fact, it would be put into the public domain. That was the other key point. And the people there had so much clout, there were several Nobel Prize winners or future Nobel Prize winners, that they were able to convince the big funding agencies to actually make this agreement into policy at the funding agencies. So what that meant was that if you wanted to work on the Human Genome Project and you wanted to get funding from the National Institutes of Health in the US or the Wellcome Trust in the UK, the other big funder, you had to agree to abide by these principles. Right? So they were able to shift from this world in which there was no reason to share data to all of a sudden this radically different world where they had every reason to want to share data. But it did take a collective agreement, and it was enforced essentially by the grant agencies. Ultimately, these ideas made their way to the highest political levels. In March of 2000, Bill Clinton and Tony Blair issued a joint statement. Essentially, they didn't actually name Bermuda, but they described the same principles in their joint statement and urged that every country in the world adopt those principles. So this is a great story at some level, and if you go to the NIH, you can go there and you can download the genomes actually for all kinds of different organisms, and it's really as a result of these sorts of agreements. But unfortunately, it's far from universal. Even if you just look at genetic data, which is a very limited type of scientific information, there's no universal agreement on sharing of genetic data. Over the last few years, there has been an incredible amount of wrangling, for example, over influenza data. So you'd think that sequencing and sharing flu data would be pretty high priority given things like the avian flu in 2006, the swine flu a couple of years ago. But no, there is no universal agreement to share that data yet. It's still very ad hoc, and there's a lot of wrangling amongst some of the leading parties. One bioinformatician of my acquaintance made, I think, the very nice comment. He said he was talking about the challenges he faces in convincing his collaborators to share the genetic data. And he said somewhat sheepishly to me that he'd been, quote, sitting on a genome for an entire species for a year. Right? So that's an entire species of animal whose genetic data had been locked up just because there was no real incentive for them to share it, and every reason in the world for them not to. Okay, so that's kind of the fundamental problem. Oh, I should say, by the way, of course, it's not just genetic data, it's all kinds of scientific data, and more generally, people's scientific ideas. There are not, at the moment, the reasons for people to share those ideas, and there's every reason in the world not to. Now, this kind of problem has been faced before in the history of science. If you go back to the start of the 17th century, so early modern science, I'll tell you a little story about Galileo and kind of the information sharing that went on in his time. So, end of 1609, Galileo has just built the world's first astronomical telescopes. And he's made his great discovery of the moons of Jupiter, and he's, as a result, got some sponsorship from the Medici family. He's sort of doing well for the first time in his life, but he's under pressure. They want him to follow it up with more discoveries to kind of, keep them famous. And in July of 1610, Galileo, who's been ignoring Saturn to this point, points his telescope at Saturn, and pretty much straight away he sees what we now know are the rings of Saturn. It doesn't quite look like rings to him. It looks like Saturn is a disk, and then there's a couple of little bumps on either side. It wasn't until years later that people realized it was really, really rings. But he knew he'd found something important. And so immediately he dashes off some letters. He dashes off letters to 4 of his rivals, including Kepler. And he doesn't tell them what he's discovered. Instead, he sends them an anagram, right? It's an anagram of a description of his discovery. So he writes down his discovery, then he scrambles the letters, he sends it to Kepler and his other rivals. And what this means, right, is that if somebody else later makes the same discovery, say a year later, Galileo can say, oh, I already knew that. Here's the key to, here's the way you unscramble the anagram. But in the meantime, he can continue working himself. So at the same time as he sends these letters, and he does that the day after the discovery, well, actually the morning of the discovery, he also sends a letter to his patrons, the Medici. But he tells them all about the discovery. There's no anagrams there, and also, beseeches them to not reveal it to anybody else. Okay, so this was sort of scientific publication in the early 1600s, and I wish I could say, it's a cute story. Actually, I can tell you this almost exactly the same story about Newton, about Huygens, about Da Vinci, a whole bunch of people, early modern scientists. They all used anagrams, they all used ciphers, and the reason was because there was actually very little culture, or almost no culture, of openly sharing scientific discoveries at the time. And so people like Robert Boyle and Henry Oldenburg was the editor of the first scientific journal, worked incredibly hard to establish the principle that, in fact, scientific discoveries should be freely shared. So Oldenburg, who set up the first scientific journal in the 1665, over the last 10 years or so of his life after that, would write to the leading scientists of the day, and he would do every kind of arm twisting to get them to disclose their discoveries. He notes at one point that one of the most effective things to do is to goad each one. So he'd find two people, two rivals, and he would ask one of them for some piece of information, and then he would send that piece of information to their rival and say, "Oh, so what do you know?" And he'd gradually drag information out of each of them in this way, which ultimately he would publish in this journal. But it was like pulling teeth. And what happened over the ensuing 150 years, basically up to about sort of 1800, is that there was a change in the culture of science, so that instead of keeping discoveries secret, it became expected that you disclose your discoveries in scientific journals as quickly as possible. So this was kind of the first open science revolution, and the way it was enforced was by tying a scientist's reputation and therefore their jobs to journal publication. Right? So it was a very clever thing to do, and it was basically done by the funders, ultimately by governments, certainly today. So that's a nice story. But as I've tried to explain today, we have a similar problem today, except now we're not talking about disclosing information in the form of journal articles. We've got that covered. Scientists are very motivated to do that because of this first open science revolution. The problem we have today is that they're not motivated to share ideas informally. They're not motivated in the same kind of way to share data. Something they're certainly not motivated to share typically is code. There's very little benefit to scientists in terms of building their career, building their reputation, to developing good tools and to sharing them, unfortunately. And that's the kind of thing which I believe we need to change today. I believe we need a second open science revolution to kind of complete and complement the first. Now, in the few minutes I have available, I'm not going to tell you how I think this can necessarily take place. I will just make a few remarks. It's a difficult problem for the reasons that I've already outlined. How do you change a complete culture? There are some encouraging signs, though. For individual scientists, it's possible to make some small motions in the right direction. Certainly, it's possible to work at least a little bit in the open, to donate a little bit of your time to doing things like working on sites such as the Wiki or whatnot. Nobody needs to spend all of their time doing it. They can just spend at least a little bit of their time. The real thing that needs to be accomplished, though, is for scientists to take these alternate ways of working more seriously. In particular, it's a question of recognition and of giving credit. So if people, go to, at the moment, if as I said before, if you put a long series of brilliant contributions on the Wiki or a similar site, it's not worth anything to you career-wise. But if people start to brag about that kind of thing or that kind of contribution on their CV, and then a discussion takes place internal to the scientific community about what value does that really have, and people develop metrics and they develop ways of measuring those kinds of contribution, then slowly a change in the culture will start to take place. That's obviously going to be a long process, and I don't think it's enough for the scientific community alone to go through that kind of process. The other thing that I think needs to happen, and it will ultimately be even more effective, is for the public at large and for politicians, for governments, for grant agencies to get engaged. In the case of this, as I said, first open science revolution, that was what ultimately actually drove change. Governments and patrons realised that it was in the public's best interest for information to be openly disclosed, and we need to have the same kind of awareness today. I told you that story about the Human Genome Project and sharing of genetic data, and at least part of what was going on there was that there was a lot of work being done in the background by the grant agencies who realized that sharing data was in everybody's best interests. And so I think a lot of progress will come basically to the extent that we can raise awareness amongst the general population of the need for more open disclosure of scientific information, and compel open release of data and similar objects, things like code, in this same kind of way. We can slowly change the culture of science. So thank you all very much for your attention.